Uh, First, thank you for the workshop organizer, and this is such a beautiful workshop and beautiful place. And yeah, today is not a nice weather, and yesterday we had very nice weather. I'm from Argonne National Laboratory, Advanced Photon Source, and so today I'm gonna talk about RIXS study of excitations in Kitaev Honeycomb model. And I mean, Professor Key is nicely introduced the Kitaev model, so I'm so relieved I don't need to explain the detail of the whole theoretical thing. Here's some recently, last year, the APS underwent the upgrade. And so we shut down the more than 1 year. And this year, June, we reopened and we now start to operate it. And so, and upgrade APS like providing new opportunity to study. And I will present a little bit about that factor. And so before and after, before the upgrade, the beam was like just regular like Gaussian like a beam, but now we have like, if you look at the amplitude of the beam, it has you can see the two peak. So overall, like a three-dimensionally, you can see the like a donut like a beam is coming in. This is because of this so-called multi-band achromat scheme and generate this beam in. And anyway, as a result, and beam for RIXS, nothing different. And so we can do the same thing. But with the coherence increases and we can do a little more, but for the RIXS, and that's not very relevant. And this is acknowledgement and at the APS and also a lot of institute and I work with, and because of that, this study was possible. Okay. So we are keep talking about this Kitaev quantum spin liquid, but where we are and keep pointing out we don't have material, and so we want to go to like an ideal Kitaev model, but we are lost in the middle, and there's so many others, and so many is just older, and so this is we are at somewhere, and so my question is, can we realize what validate the Kitaev, or maybe this system is not Kitaev and it's some kind of quantum spin liquid or some closed something. So people try many methods. First, obviously, material synthesis, and they try to make as a perfect honeycomb and without much interlayer interactions and things, but not yet successful. And also people use high pressure, like a little distorted or some manipulate the lattice and to realize this system, but not very successful. And many cases it formed the dimer states, and so it's far away from whatever honeycomb. And also applying magnetic field, and this ruthenium chloride as a famous cases, they claim they can induce the quantum spin liquid. And also another suggestion is like a laser manipulation, like a non-equilibrium states, either Floquet or like a pump probe time resolved studies. And we are all trying this all kind of thing. And so I did something, and so one of the, something I will present today. But today's talk is about, in terms of Kitaev quantum spin liquid is all failure studies, and we failed to see any obvious quantum spin liquid. But we want to see in the future, maybe we can. And that's my hope. Or we already have it and we just didn't detect it. And that's also one of the suggestions. So this is outline my talk. I will present the sodium iridate, and everybody talk, and the ruthenium chloride is the best example. But for the RIXS studies, the ruthenium is like a tender X-ray. That's not my reason, and I'm a harder X-ray RIXS guy. So I have to work on sodium iridate. And also another, by like making deficiency of sodium, you can suppress long range antiferro ordering, and we also studied. And also, I will present some polarization analysis to see, we can see the Majorana excitations, and also some time-resolved RIXS study on this hydrogen sample. I think in the iridium case, this hydrogen sample is the most close to the quantum spin liquid because it doesn't have ordering, but it has a largely disordered, camp studied well. And then at the last point in the upgrade APS, what new opportunity we can have. So I think I don't need to introduce this honeycomb lattice the systems, and it's a kind of zigzag order is happen in this system, which is long range order. The transient temperature about 14, 15 Kelvin. And so first, when we addressed this system, and we saw this beautiful, the quasi-elastic and time correlation, the equal time correlation function is like, we can see this all three direction, this zigzag ordering, like equally exist, and that demonstrates this bond directional ordering in the three direction exists. And so Kitaev interaction is in there, but what is the problem is the other interaction still there and strong enough. So what is the RIXS? And I think until now that so RIXS seems that this community is like just accepted. So it seems I don't need to explain things. And one thing I want to point out is why 5D transmetal edges is a kind of focus of the hard X-ray because 2p coao is within the hard X-ray and 2p has a strong spin-orbit coupling, and so because of that, in the balanced system we can have a spin-flip excitation because the core spin-orbit and can provide the quantum numbers. So and like a 3D transmetal can be studied well by soft X-ray. That's the reason. And if you 3D case, the K edge don't have a spin-orbit, so we cannot see the spin-flip excitation, so it's not popular now. So in terms of high resolution, and yeah, so a lot of people talk about the neutron, and neutron, we saw just data like a few millieV or micro electron volt, and yeah, we cannot beat it. And so traditionally, until now, the worldwide the possibility provide, I think, 20 or 30 millieV energy resolution, or most of the cases like 100 millieV. But ultimately, using quartz analyzer, and you can access like a millieV rhythm. And for example, in the iridium case, what I measure experimentally is about 6 millieV was the record. But as you can see here, the list and you can achieve all the 5D system is a millieV like resolution, like ultimate case, even you can go to 2 millieV. So this is using this kind of spherical analyzer, or we can use the very special setup of using flat crystal. In this case, we can analyze the polarization, unlike this spherical analyzer. So first one I studied is sodium iridate. I applied this 10 millieV analyzer system to see what it will look like, what is the spectrum. And as you can see, there's some quasi-particle-like excitation, but mostly it's a very broad system, broad excitation, which is that first when I measure and, this doesn't look like any quasi-particle magnon, because this is something special, and like a lucerne chloride is a broad feature. But this calculation is exact diagonalization, and actually it can well reproduce the experimental data. And from that, I think this comparison is not quantitative, I'm gonna say, just by looking the spectrum and what is which one is similar, and we choose this 2-parameter base and is kind of close to what we measure, and that value is about like this. And the thing is, it always has this large not large, but it's small, but it's very critical, J2 and J3. And actually those make this one is a long range order. And one interesting aspect of our study is this is a A2, A3 is the phase, and then we found that very close place there's some kind of a hidden Kitaev point. Our parameter range is not that far from hidden Kitaev point. And this A2 or A3, and if we ignore J2, J3, and this is a hidden Kitaev point, as you can see, the parameter is not that far, but it's not that close. So it's we can say it's approximate. Why not? Anyway, there's the hidden Kitaev point, and that energy scale, actually the original Kitaev term is ferromagnetic Kitaev term, but this hidden Kitaev is antiferromagnetic, and the energy scale about is 40 millieV. It's quite large. And then the sample grower suppress the long range order of sodium iridate. And as you can see, there's no heat capacity, doesn't show any transition unlike the sodium iridate. And so we studied this system, and with the expectation, we can see some difference from sodium iridate. But what we found is, okay, the zigzag order is still very robust. The two-dimensional zigzag order, we cannot kill. Yeah, we kill the 2D order, but zigzag order is just there. And so whatever that pattern come out is exactly the same with the sodium iridate. So we fail. And this is a theoretical suggestion. And so in the RIXS, you can see Majorana excitation if we probe spin conserving channel. That means polarization, just conserving channel, we can see Majorana excitation. Actually, before that, before today's talk, I thought there's a RIXS see only flux excitation, but it seems like a flux plus Majorana excitation is the one we saw. But in this theoretical study, they said at the polarization flip channel is a look at the flux excitation, and then non-flip channel see the Majorana excitation. They said, yeah, then take a look, and we can analyze the scatter polarization analysis, and let's look at, and we can see some excitations. And this is my attempts, but we do not see. And one kind of feature you can see is that at gamma point, there's a total interference, and you can see it all disappear, and at the zone boundary, you can see the intensity. So if you kind of subtract each other, you're supposed to see something. But when I compare around the gamma and around the zone boundary, and I do not see. And in this case, I use a 20 millieV energy resolution, and for the intensities, but I do not see. But one thing you have to see that the background level is rather high, and so maybe because of background. And then I tried 10 millieV, and so this is a 10 millieV data. We can see more low energy rhythm. And then when I see the difference, maybe within the error bar is nothing or something. So, but again, the background level is high, so we cannot tell. But with the maybe APS upgrade, and maybe we can try again to have, because the APS upgrade provides twice larger beam flux, and we have more chance to see. And then recently we measure. So this measurement was done at the low to theta angle to pick up the polarization conserving channel. And another try is I just put at the 90 degree, I just flip the incoming polarization. And then in that way, we can have the spin at the polarization conserving channel. And then, So if you see this red and purple, this is a spin flip excitation. This is normal. And then when I take this, flip the polarization and measure this polarization conserving channel, surprisingly, I see some high energy, so additional excitation. I don't know what is that yet. This is measured at the gamma and M, and which has some different excitation. But it's unlike this prediction, because gamma point also has something. But we are not talking about perfect Kitaev quantum spin liquid. This is based on the perfect Kitaev quantum spin liquid, but in the real system, we don't know what is the quantum spin liquid system. But the important message here, in the polarization conserving channel, we have additional low energy excitation, which cannot be spin flip excitation. And so I think that there's some, if this suggestion is right, and this may be some kind of delocalized minor excitation. And this one taken at the low base temperature, like 4 Kelvin. But if we study like a little temperature dependence, okay.
No, I just had a
This one?
for the gamma point.
You mean this intensity?
Yeah. Why is it so much farther?
Oh, because this elastic is much larger.
Oh, okay.
Yeah, yeah. Because elastic larger, because when you have this spin conserving, that means the Thompson scattering is getting in, you have elastic intensities. Yeah, and so we will take more data, and then we will see this polarization conserving channel has this kind of momentum dependence and also temperature dependence, and this cannot be phonon, because at the 90-degree phonon intensity is so small, and so I think this is very promising. And so another try is like a time resolved or like a floquet or laser manipulation of the system. To do that, we went to free electron laser facility, and we achieved at this time 90 millieV. We found we can improve a little more resolution, like we can achieve like maybe 30 and 40 millieV. Anyway, we successfully achieved, and we like a 15-minute data, you can have the spectrum. So it's not very time consuming. And this is 15 minutes. You can see this is as a single shot experiment. And this is the experimental setup. Anyway, we just did it, and so we didn't analyze it, and also we have a lot of technical problem. So this is just, I'm just showing this is our try, and again, this is another failure. So when we use 140 nanometer, and as you can see, we do not see any time resolved signal, and it's frustrating. So in the hard X-ray case, time resolved is what is the hard part is the probing depth of the laser and X-ray is such a big difference. So we have to use a very grazing incident, and then make an experiment kind of very challenging. And so anyway, even 0.5 degree, we do not see anything. And then we use 19 nanometer, and finally we see some, but at only 0 time delay. That means it seems that this one response only like a floquet like a response, not like you pump and it's a kind of long lasting effect. And this is currently we think. But anyway, there's a response, and if we solve some technical problem of probing depth of something, actually we can have more meaningful data to show. But yeah. And as the last part, and so APS upgrade, it's like a focus on brightness and coherence flux. Coherence flux is not that meaningful in our inelastic X-ray scattering, because after scattering and all the coherence information is gone. But brightness matters a lot, and also maybe people know, but it's usually synchrotron beam is like very horizontally long and vertically like small. But after upgrade, the beam become more like a circular. So it provides, anyway, so this is some measurement of emittance and also coherence length. Now the horizontal, the transverse, the coherence length is 50 micron, and this is pretty good. And another possibility, because the beam is small, and so now we can use, it's meaningful to use the jump plate to focus or some manipulate the wavefront. And another interesting possibility is that we can make a twisted X-ray, which is somebody called orbital angular momentum. And orbital angular momentum, it has orbital angular momentum, and so interaction with the matter is different. And it's my point of view, when we think about the vector potential, and when we use the dipole approximation, okay, we have dipole approximation. We only see the dipole transition, dipole excitation, dipole order. But by having this twisted and as a vector potential is additional this R term, it make R, it has a quadruple term, is the main one. And so we can see high order scattering more effectively. The high order means, I mean, today we talk about the two spin flip, and now this, if we use this beam, I expect two spin flip is more dominating than the single spin flip. But that's just the experimentalist, some expectation. Theoretically, I do not know, because there's not much theoretical work. But by using this new wavefront manipulation, I'm expecting new interaction. That means a new excitation. And maybe we can apply this to this Kitaev Quantum Spin Liquid system, and we can see maybe it's a better way to observe not just this single spin flip excitation, but it's a multiple excitation. And this is a kind of ongoing study, and we do not make yet, but like about 10 or 15 years ago at the APS, somebody made it, so it's possible. So if we make a spiral jump plate, which we can make in our facility, and so this is a become possibility. And here we have a lot of good theorists, and I urge kind of to look at the possibility of using this kind of X-ray and what kind of like a scattering cross-section we can have, and not only this system, and there's a lot of chiral system. Chiral system is obvious. When we use the helical dichroism, maybe we can observe something new, but here my focus is the Kitaev Quantum Spin Liquid system and the possibility of looking Majorana excitations. So, yeah. And one of some abnormal response, and you can see, and this is nothing to do with the jump plate, and just use the left and right, and just the circular dichroid. No magnetic field, just circular dichroism. And we don't expect anything particular in this system. But when I measure this, and one thing is odd to me is that this DD excitation, which is splitted by trigonal distortion, and its energy is a little bit shifted. It's a very tiny little, but I think if you see this difference, it's up and down, that means overall like a little bit, there's some dichroism of the D. Yeah, D is, and here's you don't have this. This is not DD excitation. This is a so-called like electron hole pair, some resonance mode. And another interesting is this like a so-called is a broad magnetic excitation area. We can see some dichroid responses. I don't know what is that, but so this Kitaev quantum liquid system, and when we use circular dichroism, which means it also has different transition probabilities, and it may have this kind of. Anyway, I will show you this is data because if by manipulating X-ray, we can have new response from the system. And I hope we can have more solid interpretation, but I don't have now. Yeah, I think this is conclude my talk.